Nobody at school can avoid the 3 laws of Isaac Newton, and that's quite alright because they form the basis for all physics. It's really impressive how mathematically accurate Newton is in describing the motion of objects. By the way, the physicist got his 3 principles only from observing nature, and even today nothing works without Newton's laws. Only they enable us to describe and understand most of the everyday phenomena physically. Wow, welcome to Clixoom Science Fiction. Don't forget to subscribe to the channel and never miss a video again. 1, 2, 3. Isaac Newton is probably one of the most important scientists of all times. A well-known quote of his is, "What we know is a drop, what we don't know is an ocean." He actually founded modern physics in the first place, so he made sure that our drop of knowledge became at least a little bigger. But from the beginning, in 1687, Newton published his book with the name Mathematical Principles of Natural Philosophy. Here he combined previous researches, like for example Galileo Galilei for acceleration and Johannes Kepler for planetary motion, and thought them through. His ambitious goal was to describe exactly how objects move and influence each other. This was a huge challenge because terms such as force or mass were by no means as clearly defined as they are today. What was missing was a uniform mathematical, scientific, technical language. It was Newton's work and his exact description of things that made these concepts as clear as they are today. A milestone in modern physics. And that brings us straight to the first law. In short, it means as much as everything remains as it is if you don't do anything. Physically correct. This is what it sounds like, how Newton himself wrote it down. Everybody persists in its state of being at rest or of moving uniformly straight forward, except insofar as it is compelled to change its state by force impressed. In short, an object that does not move will not move until you exert a force on it. But it also means that an object will keep moving as long as you don't exert force on it. At least the first part sounds really easy and comprehensible. Let's look at an example. As long as nobody kicks against the football, it simply remains lying around somewhere. So far so good. But that brings us to the second part of the first law. According to it, once a football is in motion, it should keep moving. Everything we know from our everyday lives will come to rest at some point, no matter whether we threw it, kick it, or just nudge it. So, does that mean that Newton's law is useless? No, because Newton is right, but the forces that act on the ball and eventually slow it down are not directly visible to us. In concrete terms, I mean, for example, air resistance or friction force with the ground. Nevertheless, Newton's first law seems illogical to us, at least at first glance. But I can assure you that the whole thing with a ball in a vacuum, for example in space, looks quite different. Here the ball moves on and on without ever coming to a halt, and with that we have ticked off the first law of Newton and come straight to the second. It cannot be simplified as easily as Newton's first law. Nevertheless, it is worthwhile to understand the second law, because it has an incredibly important meaning for physics. It is the basic equation of mechanics. The second formula is actually always in use, namely when something is moving somewhere, but actually also when nothing is moving, because one thing is certain: some forces are always at work, and that's exactly what Newton's second law is about. What happens when a force is acting? Newton himself had formulated the law in this way: the alteration of motion is ever proportional to the motive force impressed, and is made in the direction of the right line in which that force is impressed. Or, in modern terms, the change of momentum of a body is proportional to the impulse impressed on the body, and happens along the straight line on which that impulse is impressed. So Newton's second law describes how the object changes its motion when a force acts. But it says much more, because with the phrasing alteration of motion, Newton means that we would describe today as the change of momentum. The second law means in summary that every force corresponds to a change of the momentum. The direction in which the force is directed also corresponds to the change of direction of the impulse. In short, force is equal to change in momentum. And this goes beyond what many may have remembered as Newton's second law with a simple mnemonic. Force equals mass times acceleration. Sometimes, actually, ever so often, this is true, but not always. That's why we have to pay attention. Since we have just said that force equals a change of momentum and that momentum is mass times acceleration, it is so decisive importance that the momentum change can result from 2 or even 3 different events, namely from a change of speed or, however, from a change of mass. A change of mass as well as of acceleration is also a possibility. Then both will change. Often it does not happen that the mass of an object changes, but it can happen. Of course, when we kick a football, its mass does not change. So here the simplified sentence also applies. Mass times acceleration results in force, because the speed of the ball changes in this case, and that is the acceleration. However, this is not the case with rockets, which burn a lot of fuel during their flight into space and thus change their mass enormously. Here, not only the speed changes like the football, but also the mass. And with that, we have already learned the first 2 of Newton's laws of motion. Now, take a deep breath, because the third law is a bit more complicated and not as easy to get your finger on as the first 2. Let's let Newton have his say. He had phrased his third law as follows. To every action there is always opposed an equal reaction, or the mutual actions of 2 bodies upon each other are always equal and directed to contrary paths. Translated into today's language, this means that forces always occur in pairs. When body X exerts a force on body Y, a force of the same magnitude from body Y also acts on body X. This force is opposite. The emphasis is on the fact that forces always occur in pairs, but the reminder to this third law, which you often hear about in everyday life, is a little too short. Action equals reaction. Let us forget this, because it is by no means the case that one force is the cause to which another force then reacts. Rather, it is about the interaction between at least 2 objects, and these have forces as a result. This means that when I press my hand on the table, my hand is also pressed by the table. That's really the way it is. But it is not the case that I first press my hand on the table and that it then presses against my hand because and after I pressed my hand on it. So the second force is no reaction to the first force. Another minor complication results from the term equal in size, because for each force there should be an equally great counterforce according to the general phrasing. But how can this be true if, for example, a tiny fly pops on the windscreen of a racing car? According to this, the car would exert a force 1 on the fly, and this in turn would exert a force 2, which is opposite but the same as force 1. The race car can still race undisturbed, but the fly remains crushed, and indeed, both forces are the same, but the acceleration is different. This is composed to force through per mass. But the mass of the fly is very low compared to the car, and therefore its acceleration is much higher. Thus, it has no chance at all in the collision with the car. The car, on the other hand, hardly accelerates and can continue undisturbed. I would therefore recommend you to use your modern terms, especially in Mr. Newton's third law, and to work, for example, with the so-called conservation of momentum. According to this, the entire impulse is always preserved in a closed system. If you remember Newton's second law once again, every force is a change of momentum. Since the total impulse does not change according to the third law, i.e. remains equal to zero, the sum of all acting forces in a system must also be equal zero. So, logically, there's an equal force for each acting force which counteracts. So, now we can state that Newton and his laws have created the foundation on which modern physics has developed. Even if the Newton's laws no longer apply in the exact form of that time, since then physics has been extended, for example, by the theory of relativity and quantum mechanics, nevertheless, Newton's three axioms still enable us to describe and understand most of the physical phenomena of our everyday life. Chapeau, Mr. Newton. The theory of the world is explained in this video here. E8 theory, a simple theory of everything. Just click right here and don't forget to subscribe to the channel to never miss a video again. Stay tuned and see you soon.